This is going to be a tutorial about significant figures. In order to start off, we need to talk about what's called uncertainty in measurements. So measurements are basically made with lab equipment. As you see in the picture, graduated cylinder is probably the most accurate piece of equipment you'll have in the lab to measure a volume's liquid, a liquid's volume. A beaker does not do that great of a job, though the beaker can be used to estimate. And if you notice in the picture, there is a piece of equipment that has a really long neck seen right here. That's called a volumetric flask. That is a very accurate piece of equipment that does accurately measure liquids, but you will not have access to that on a daily basis. So measurements are made with equipment, and our equipment, have some sort of gradations on them, the markings on them. So you get to make a measurement yourself, and when you make that measurement with whatever you're using, even if it's a ruler, there's always some sort of estimation. So you get all the digits that you're certain about on that scale, plus one extra guess, which we call the estimation place. So a measurement has all the certain numbers plus one uncertain number, which is the estimated place. So let's practice this. Here's a blurry image of a pencil on a ruler. Yes, it's blurry. Nothing's wrong with your iPad. Do not adjust. And let's see if we could take a measurement to the way edge of the lead. And if we look right there, let me see if I could do a little drawing here. Oh, that's a really bad line, but you get the picture. Right around there is where the measurement should be taken. And so if you notice, for sure this measurement has 8, I don't know, let's just say we're talking about centimeters, has an 8 in it. If I look at the rest of the scale, I notice back here that there's a 7 and here's an 8. And these are the increments seen here in between, these increments. So if I figure out the scale from here, this is 7, this is probably 7.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.98. Therefore, I know for sure that this is 8.1 and 8.2. So this measurement for sure is 8.2. How do I know that? I actually see a marking on here. I'm highlighting it right now to show you that this is 8.2 something. Now, that something is what we call our estimated spot, seen right here at the end. Well, it falls between 8.2 and 8.3, so I'm going to say, I don't know, 8.25. This is the estimated. You only get one estimated spot. Whatever you want to make it, you can make it. If you saw 8.29, that's fine. Do whatever you'd like in that spot. That is your judgment call. So in other words, for sure we can all say that the first 2 digits in the measurement are the same no matter who reads the scale. Therefore, those digits are called the certain numbers, right? And that was the 8.2. We're certain about that. The third digit we said is the estimated one. Therefore, we call that an uncertain number or an estimate. So like we said, you could have 8.21, 8.22, 8.23, 8.24, etc. And now on to significant figures, which is the main point of this lesson. They're basically the numbers that are recorded in a measurement, and they're all the certain ones plus the uncertain digit, like we just saw in our previous examples. They're called significant numbers, or sig figs, or significant digits, or sometimes I abbreviate them as SF. So the number of significant figures for a measurement is determined by the uncertainty of the measuring device. What that's basically saying is your measurement and the number of sig figs you have is only going to be as good as the device you're using. So let's see what that means in our examples ahead. If we look at the rules and we want to look at a measurement, and we say, okay, let's say we have a measurement. How many digits in that measurement are actually significant? There are 4 rules. And these 4 rules are, 1, non-zero numbers in a measurement are significant. So for example, if your measurement has a 1 or a 2 or a 3, 4, you get the picture. Non-zero numbers. These are all significant digits. Second rule. Leading zeros are not significant. Leading zeros are the zeros that come in the beginning, as seen here, of a measurement. These digits are not significant. They're placeholders. We can't get rid of them. So they have a purpose, but in our measurement, they're not significant when it comes to reporting which digits are significant. So how many significant figures are there in this calculation, in this number right here? I've got 1, 2, seen back here, the 3 and the 5 are significant. So there are 2 digits that are significant. So I say 2 sig figs in that number. Let's look at the third example. Captive zeros or trapped zeros are significant. If you notice, these zeros are trapped between 2 non-zero numbers. 1 and 4 are non-zero numbers. They have trapped the zeros between them. If a zero is trapped, as seen here, they are significant. Both of them are significant. So, how many significant digits are there in this entire measurement? Well, the 1 is significant because it is a non-zero number. The zeros are significant because they're trapped. And the 4 and the 7 are significant because they're also non-zero numbers. So there are 1, 2, 3, 4, 5 digits in this number that are significant. Trailing zeros, rule number 4. They're not significant unless a decimal is present somewhere in the number. Doesn't matter where it is, the decimal has to be present. So what is a trailing zero? They're zeros that come at the end of a number. See here? At the end. These are trailing. They're at the end. This is not trailing. That's called a leading zero, as seen in rule number 2. So we're not talking about that zero. So trailing zeros, they're only significant if there's a decimal present somewhere in the number. And here we go, there's a decimal present. So therefore they are significant. So how many significant digits are there in this number? Well, the 0 is not significant, it's a placeholder. The 2 is significant, the 3 is significant, and the 2 zeros are significant. So there are 4 sig figs. Let's take a look at the next example right here, the 100 with a decimal point at the end. These are trailing zeros. They're at the end of the number. There is a decimal present. Look at rule number 4. The trailing zeros are not significant unless there's a decimal somewhere in the number. Well, here's the decimal. So therefore, these are significant. Don't forget, so is the 1. It is a non-zero number, so 1 is significant and the 2 zeros are significant for 3 sig figs. Exact numbers are numbers that are counted. So if I put 12 eggs on a table and I say, tell me how many eggs there are, you would count to tell me that there are 12. If at any point you notice that in lab you're using counting as a way to record a measurement, then there's a specific sig fig rule for this. We say that there are infinite sig figs, meaning if I said 12 eggs, then it's a perfect 12, meaning behind the decimal there would be 0, 0, 0, 0, 0, 0, 0, going on and on and on and on and on. As you can see, I ran out of room. Meaning it's a perfect 12. It's not 12.1, it's not 12.00001. You get the point. So therefore, there's an infinite amount of sig figs, meaning unlimited. And so the way we record this is by using the infinity sign, which looks like an 8 that fell over. All right, now, what about calculations? So we talked about how to count to see if there are sig figs in a measurement. But now we're going to talk about the rules when we calculate. So there are specific rules when you calculate with significant digits. We're first going to talk about addition and subtraction. And we clump those together because it's the same rule. Okay? So if we look at our example seen here, this first example right here, I'm adding these two numbers together. They're measurements because we're in science. And I want to know, how do I accurately record my answer to the correct significant figures? How do I correctly record that? Well, if you look at this measurement seen on the top, wow, whatever piece of equipment was used can go out to many places. But you see this one here? This measurement only went to the hundredths place. So I don't know what's in these spots over here. I don't know. And because I don't know that, I can't record those spots down here in my answer. That would just be misleading. So 0.31 limits me. Therefore, when I add and subtract, my answer has to be cut off to match the number that limits me. There's only 2 places after the decimal, so my answer can only have 2 places after the decimal. So before I cut this answer off, I need to round. So I'm going to cut it off there. So look one place next door. What's next door is higher than a 5, 5 or higher, then I round up. So 23.87 turns into 23.88. That is the correct answer. Same thing with subtracting. If you look at this example, I have 110 minus 24.5. And when I do that basic subtraction, I get 85.5. But now I want you to record it with the correct sig figs. Well, let's take a look at these measurements. Wow, 110. This piece of equipment didn't even have a tenths place. That's a pretty poor piece of equipment. Whereas this equipment did have a tenths place. But the thing is that I can't record this answer to the tenths place because I don't know what was back here. So when I write my answer, I can't have a decimal place. I can't have a tenths place. So when I subtract these two, I get 85.5, and I can't have this decimal place right here. But before I get rid of it, I need to round. So I look at it to round. If it's a 5 or higher, I round up. So 85 rounds to, let's erase this answer because that's no good, 86. Not 90, 86. That's your answer. This is the last rule. We're almost done. Multiplication and division. They have their own rule that's different than addition and subtraction. You want to go to the least accurate number. Well, what does that mean? So this is kind of easy. We're going to go back to asking you how many significant digits are in 56.89. You should have said 4. How many are in 235? You should say 3. Whichever one's the lesser of the two, 3 is smaller than 4, your answer needs to mimic that. So when I multiply these two by each other, I first get this answer, so always write down the first answer. Now you want to record it to the correct number of sig figs, which means I'm going to put 3 significant digits, 1, 2, 3. Before I cut this off, I need to look next door to round. That's a 6. So 13,369 turns into 13,400. If you notice, I still have to keep the place values. I insert zeros to keep the place values. If I got rid of that and I accidentally wrote 134, well, 134 is a very different number than 13,400. These zeros are not significant because they are trailing. Same thing with division. Ask yourself how many significant figures are in this number right here. And that's 3, 4, 5, 6, 7. I count 7. How about in this number? None of these leading zeros are significant, so just 2. The 2 and the 6 are significant. Here's my big answer when I divide. And now I want to cut it off to 2 sig figs. Here's the cutoff. I look next door. It's an 8. 5 or higher rounds up. But I need to make all of these zeros to give it a placeholder. None of these zeros are significant. They just hold the place. So there are 2 sig figs seen here. If you are confused, do not worry. This is your introductory lesson. We are going to cover this more in class. Please feel free to watch this video again and practice them on your own.